Hello everyone, I'm George Wilson, and I'm here to talk to you today about laws! Yeah! Alright, I work at QFPL, the Queensland Functional Programming Land, under Data 61, and I think about laws all day, and sometimes write code as well. Alright, so let's get right into some laws. I think some of you might have seen some of my other talks, and if you have, you know that I always get very excited about laws. You know, I'll put some crazy bit of code on screen and say, look, laws, and then I'll move right on. Right? Today there will be no moving on. There will only be laws. Let's get right into it. I want to talk about monoid. Yeah, it's on the screen there, good. Monoid, okay? We're going to spend a lot of time looking at monoid. We're going to get very comfortable with monoid. Okay, so this is a type class in Haskell. Monoid, it has two things in it. It has the bottom thing there. Excuse me, the bottom thing there is a binary operation that takes two things of type M and somehow produces something of type M. So it'll usually combine these two values in some way. Okay? And the other thing a monoid has is this thing called mEmpty, which is just some single value of that type. Okay? But this isn't the whole story, because monoid has laws! Yeah! Alright. Which laws does it have? Monoid has three laws. It has the left identity law, the right identity law, and associativity. These are awesome. Okay? So left identity says if we combine mEmpty with anything on the left, we get back our anything. Okay? Right identity, you may be able to already guess, but says if we combine anything with mEmpty on the right, we get back our anything. Okay? So mEmpty acts as this sort of identity element, or people call it a neutral element, okay? When used with that operation, mEmpty doesn't change the result. Okay, and associativity is great. It says that if we're combining, you know, a few things here, in this case 3, we can combine x with y and then combine that whole thing with z, or we can combine x with the result of combining y with z. Alright, let's look at an example of a monoid. Addition. Addition of integers in this case is a monoid. So our empty element is 0, okay, and we combine two of these by adding them. Alright, so if you add 0 to anything, you get back the anything. Alright, so left identity says that for any y, if we add 0 to y, we get back y. We can pick any int we like, let's say 5, and we know that 0 add 5 is 5. Alright, that's what left identity says when we're interested in plus. Right identity says that if we can pick any x that we like, and if we add 0 on the right there, then we get back, in this case, 7. Here's associativity, right? So it says that if we're adding 3 to 4 or 5, we can add the 3 to the 4 first or the 4 to the 5 first. And whenever we show associativity, we show it with parentheses, and that's rubbish. We've got to stop this. All right, associativity is about trees. Oh, I've gone off the end there. I hope that, in this case, it doesn't hurt too much, but hopefully it doesn't come up later. Or maybe I can fix that. Hang on. No, it didn't fix it. All right. Yeah, so associativity really says that these two trees of computation are the same. We can add the 3 to the 4 and get 7, then add that to the 5 and get 12. Or we can add 4 to the 5 and get 9, and add 3 to that and get 12. Okay? So these two trees of computation are the same. This is what associativity is about. It's not about parentheses. I want you to think about trees when you think about associativity. And you're like, so? Who cares? If I can just move a bit of tree around, what's the big deal? Why is George up here yelling about all this rubbish? And it's because, when we look at associativity, we just say, look, you can do this one little bit. But what we're really trying to convey is, if you have some ginormous tree, you can restructure it however you like. So you could balance the tree. Now, you can't swap the left and the right, but you can rebalance the tree however you like. So you could balance the tree. You could put everything to the left, even off the edge of the slide. Or you could put everything all the way to the right. And associativity says that all of these trees are the same. That's very cool. So think about trees and think about very big ones. That's the power of associativity. Now, monoid is a very good abstraction, and because of that we can write useful functions in terms of it. Here is such a function, it's called mconcat. And mconcat says that if I have a list of m's, I can combine them all using our monoidal operation into a single one. That's what mconcat says. Let's write it. Let's go ahead. So mconcat takes a list, and it says, well, the list might be empty. If it is, we give back the identity element. Or if the list isn't empty, it has a head and a tail. So the result is the head appended onto the recursive result of mconcatting the tail. A very natural recursion over lists to define this function. Okay, so if we have some numbers, like 1, 2, 3, and 4, we can mconcat this list, and it adds together all the numbers like this, and we in fact get 10, which is what we want. Did you notice that this computation is all associated all the way to the right? And there's an extraneous mempty there. That's because when we wrote mconcat, we wrote it very naturally against the structure of list. And the structure of list is that it is recursive to the right. And so by writing mconcat in terms of the structure of list, we've ended up with a right-associated computation. That's only okay to do because it's associative. Okay, so with the power of associativity, we wrote this function in the most natural way, and it's just as valid as any other implementation. What if we didn't have associativity and we still wanted to write something like mconcat? Well, here we have our not monoid type, and we'll have to call it mconcat R, and we're going to have to remember this one's associated all the way to the right. Remember, if we don't have associativity, then putting everything all the way to the right might give us a different answer than if we had put everything all the way to the left. Oh, gee, so we better have another function. So this is mconcat L, okay, and this does the same thing, except it associates everything all the way to the left. It's a less natural to write function. Thankfully, it will fit on the slide. But now whenever we want to combine a list of these not monoid things that don't have associativity, we're going to have to think really hard, oh, gee, do I get the answer I want by going all the way to the right or to the left? And in fact, this isn't very valuable to have because you might as well just use a fold R or a fold L. Okay, so fold R and fold L are just better than our non-monoid thing because they have more general types. The thing on the left and the right can have different types in fold R or fold right. Okay, so, you know, if we lost our associativity, suddenly our world of derived functions becomes quite murky, and in fact, they're just less valuable than some other functions we already had lying around. Okay, so I want to say that laws give us freedom when we're working in terms of our abstractions. We saw that we were able to write a function mconcat in terms of the monoid abstraction. I'm very sorry, and we were able to write it by recursing over the structure of a list in a way that's very natural to do when we're thinking about a list. And associativity just said, that's okay, you can do that. And so this is some of how I use laws. You know, if I know that if I have a certain law, I will be able to write something in a way that's convenient for me at the time. And that's really powerful. Let's look at another monoid. This is called the list append monoid. So we can append lists, we can take two lists, and we can just sort of stick them together. Okay, we saw that in the keynote this morning. And how do we do it? Well, to append a left list onto a right list, what we do is we walk through the left list and we say if the left list is empty, the result is the right list. Okay, we're done. If the left list is not empty, it has a head and a tail, so the result is appending the head of the left list onto the recursive result consing the head of the left list onto the recursive result of appending the tail of the left list to the right list. Okay, and this turns out to satisfy all the laws we care about. If we append the empty list onto a list, or if we prepend the empty list onto a list, we get back the same list. List append is also associative, so if we, you know, we can do the parentheses, or better yet, trees thing. Okay, we're going to look at this monoid because it's very cool. So let's write a function with this monoid. Now, in Haskell, our strings are just lists of characters, so I can use the list monoid to work with strings. So I'm going to write a greeting function which takes a name and gives back the string, hello, name, how are you? But this greeting is for a Lisp programmer. And so I've surrounded it with parentheses. Tim mentioned earlier conference card bingo, right? Lisp paren joke, right? You've just ticked off another box. All right. What I want to do now is I want to refactor this function a bit, because I notice there's an important thing that I want to be able to reuse. I talk to Lisp programmers a lot. We have correspondence back and forth. So I need to put parentheses around a lot of sentences. So I can pull out this helpful little function called between, which takes an open, a close, and an X, and puts the X between the open and close. Okay? Now I can refactor my original greeting function to say, between two parens, put hello name, how are you? So we've pulled out this little function between, and it turns out between depends only on monoid. Between doesn't know anything about strings. Okay, so this function works with any monoid. It's very cool that it worked out that way. And it's reusable. Don't believe me? We can use it again. So now we can say between two parens, between hello and hi, how are you, put the name. Maybe you wouldn't write it that way, but believe me, you can reuse between. So that was a nice little refactoring, and I enjoyed doing that. Did you notice we used associativity? Originally, when we were constructing our sentence there, our tree of computation looked like this. All right, we were appending a paren onto hello, onto name, onto how are you, onto another paren. But when we pulled that function between up to the top level, suddenly the actual greeting bit itself became a little subtree off to the left, like this. Okay, so in that little refactoring there, we actually required associativity. If appending strings wasn't associative, that refactoring would have broken the program. Okay, so associativity is really cool. It lets me refactor things. And in fact, I think you're even using it when you don't know you are. I think you're using associativity more than you even think in your general day-to-day refactoring of code. Okay, so that's why laws are so great. You're already using them. I'm just telling you that you already love them. Right. So I think laws let us refactor more. We were able to pull out the between function. We couldn't have pulled that function out without laws. And they let us reuse more. We were able to reuse the between function. In fact, we could have reused it in a context that had nothing to do with strings. Okay, because monoid is an abstraction. Okay, so we really got some value here. And now I want to talk about a problem. It's a devious problem. It's called the left associated list append problem. And it makes me sad. So, the left associated list append problem. That goes off the slide, but it doesn't matter. All right, when we walk through lists, when we append lists, we walk through the left list. Okay, so let's append these three lists, 1, 2, 3, to 4, 5, 6, to 7, 8, 9. But let's left associate. Okay, so we're going to append the left two lists first. Let's see how we do that. Well, we go through the left list. We see 1. Okay, we'll allocate a 1, 2, 3, and then we just point at the right list and say, all right, so now we can garbage collect our original 1, 2, 3. So now this thing, 1, 2, 3, 4, 5, 6, is now our left list in another append. So now we're going to append 1, 2, 3, 4, 5, 6 to 7, 8, 9. So we go, well, 1, 2, and so on, you know, and then we've appended 1, 2, 3, 4, 5, 6, 7, 8, 9. The problem with this is we've wasted a bunch of effort. We've walked through 1, 2, 3 twice. Okay? And the reason we did that is because our appends were left associated. Okay? Now we got the right answer. Laws say that the associativity law of list append says we can associate these to the left or right. But the law just says we're going to get the right answer. In this case, one way of associating it turned out to have better performance than the other. So if we have, so in this case, it didn't end up costing us very much. But if you can imagine if you have a lot of lists that you're appending, all associated to the left, and they're very long lists, then you're just going to be walking through, perpetually building up a bigger and bigger list in the left position, which is where you pay for. So this is why left associated list appends are a problem. In fact, they run in n squared as opposed to n. That's a huge problem. What are we going to do about it? Well, I'm going to introduce you to a type that does something about it. We can fix the left associated list append problem with a type called dlist. Okay? And I'm going to tell you what dlist does, and I'm not going to tell you how it does it because it's a short talk slot. All right? So you're not going to learn how dlist works, but you're going to learn the amazing wonders that it performs. So dlist is a data type. It has a monoid instance. Yay! That obeys all the laws. And dlists are really incredible because they append in constant time. You can take two dlists, no matter how long they are, and append them in constant time. You say, oh my goodness, George, lists that append in constant time? These are awesome. I want these everywhere. This is how I'm going to live the rest of my life. How do I get a dlist? Well, you get a dlist from a regular list, like a normal list. Okay, using the from list function. Okay? And you can from list a list into a dlist in constant time as well. And then when you're done delisting, then you call toList, and you can turn your dlist back into a regular list, a normal one, yeah. Now this takes n time. You can't do everything in constant time, all right, but you can sometimes play funny games to make costs go elsewhere. So let's use dlist to optimize some left associated list appends. So instead of having this deeply left associated list append here, which is going to take n squared time, what we can do is we can instead call from list to turn all of our lists into dlists, then do our great big left associated append, and then we can call toList on the result of that and turn it back into a regular list, okay, and this turns out to be linear time. So we've appended all those lists, even though it was all left associated, because we went through dlist to do it, we ended up getting the optimal time for appending lists. So that's really cool. So instead of having, n squared going from list to list with left associated appends, what we do is we call from list, which is constant time, but we have to do it on all of our lists. So it's actually n. Okay, we call n from lists, and to turn all our lists into dlists. Then we do our left associated appends. Each of those is constant time, but we're doing n of them, so it's n. Right? And then on our resulting dlist that we've concatenated together, we call toList, and that's n as well. Okay? And if you know anything about complexity theory, you know that n plus n plus n is n. And so by going via this intermediary of dlist, we've been able to turn something that would otherwise have been n squared into n. We've optimized the program. Well, what is optimization? I would say perhaps that optimization is when we alter a program to get the same answer more efficiently. That's laws! Laws are all about altering the program but getting the same answer. And I want to show you exactly the laws that were at play when we went through dlist. So dlist has all sorts of cool properties that we can start to talk about. So from list, the function from list, which creates a dlist, has what's called a left inverse, which is toList. All that is to say, if I call from list on a list to get a dlist, and then I call toList on that dlist, I get back exactly the same list as I started with. Okay, so toList is a left inverse of from list. Okay? The other interesting point that I want to talk about, or the other law that dlist related things have, is that from list is a monoid homomorphism. You'll say, George, what on earth is a monoid homomorphism? That's an excellent question. I'll try to answer it. So, from list is a function which takes a list and gives back a dlist. List is a monoid, and dlist is also a monoid. Okay? So a monoid homomorphism is a function that goes between monoids. But not just that, it has to satisfy some properties, or what we might call laws. So it has to, informally, it has to preserve the monoidiness, right? Or to try to put it more formally, if I call, in this case the function is from list, if I call from list on the empty list, the identity element for list append, I should get the identity element for dlist append. Okay, so we're preserving the identity across this transformation between monoids. And the other one says that if I append some lists and then I call from list on them, that should be the same as calling from list on each list and then appending those two dlists. Okay, so this is like a function that translates between monoids, preserving the structure of identity and appending, and associativity as well. So from list is a monoid homomorphism, and now I want to show you. Imagine we have some list like this, x, append y, append z. Well, because toList is the left inverse of from list, we know that we can put toList and from list out the front here, and then we haven't changed the answer, right? Because from list is a monoid homomorphism, I know that if I have from list outside of a big chain of appends, I can rewrite it to being a bunch of appends of from lists. Okay, so now I can have toList of from list of from list from list, and this is our optimized form. Okay, so we got from our starting form, we applied some laws, or some some transformations that were part of laws, and we were able to get to this optimized form. Okay, so that's how the dlist trick works, and that's how it gets the right answer. Okay, so now you say, George, I'm really sold on laws. Laws are really cool. I would shudder to think what a world would look like without laws. And unfortunately for you, I'm going to show you such a nightmarish hellscape as that. Okay, let's look at a world without laws and see what tragedies befall us. This is the default type class. It's got one member called def of type A. It's for things with a default. I don't know what that means. There are no laws. There's a default list, it's the empty list. That's probably pretty reasonable, I suppose. There's a default int, it's 0. I think that's pretty crazy. Because imagine you're an addition-minded person and you get up in the morning and add some things, then you go to bed, right? Fine, 0 is the default integer in your world, right? But if you do anything else with integers, 0 is a terrible default. If you like multiplying, if you work in the product department, if you like multiplying, then 0 is a terrible place to start because you can never get away. Let's not even talk about if you're interested in division. Okay, so I think the default type class really isn't very good. The instances are just picked arbitrarily. Maybe we can still write a function in terms of that interface. So let's try. This is a function called orDefault. And it says if I have a maybe A and there's a default A, I can get an A. If the maybe's full, you get the one that was in there. If the maybe's empty, you get the default. That's a function you could use, I suppose. I've got a better one. Or else. Or else takes an A and a maybe A and gives you an A. And it says, well, if the maybe was empty, you get my A. But if the maybe was full, you get that A. Okay, and or else is strictly better than orDefault. Because orDefault, it takes the default type class, which is just an arbitrary choice, whereas or else puts the arbitrary choice in the hands of the user of the function. They could even choose to use the default from the default type class if they wanted to. Okay, so or else is better. So we tried to write a function in terms of default, and then I could just pull a better one out of my hat. Alright, so we've been looking at Data.Default, at class for types with a default value. I want to take a look at a competing library, which is called AcmeDefault, which is a class for types with a distinguished, aesthetically pleasing value. It defines the same default type class, but it gives different instances. So the default int64 is -1. There's a comment explaining why. Why? Because that's the biggest negative number. This is as good as saying 0. In fact, this is arguably better because it's documented. There's a default bool, it's false. Why? Well, the library author asked his friend and said, hello, do you have a favourite Boolean? And his friend said, no, I don't have a favourite Boolean. And he said, no, that's false. Right? And there's an issue on the repository. This code hasn't made it into a released version yet, but there's an issue on the repository that says perhaps a good default string might be Moby Dick. But I can't fit it on a slide. Okay, so you're all saying, all right, laws are amazing, they're wonderful, they let me do cool things, and a world without them is topsy-turvy. How would I know whether I obey the laws? If I'm making my own monoids, how would I know? Maybe you could write a proof or something like that, but I use property-based testing. All right, so there's a library called QuickCheck for property-based testing, and there's a library for working with QuickCheck called Checkers, which defines a bunch of properties for these common abstractions. Okay, so Checkers is a really cool library. It defines something. It defines a function called Monoid, which says, tell me a type, and I'll give you a bunch of tests that test whether it's actually a monoid. We can do the same thing for Functor, and all the same law-having type classes that we all know and love in Haskell. Okay, so we could make a totally dodgy monoid instance for subtraction that breaks the laws, and then this library gives us the power to test it. So we can test whether addition's a monoid, we can test whether subtraction's a monoid, and indeed, according to 1,500 tests, sum is like adding things is a monoid, and according to 504 tests, subtracting isn't, although it does have a right identity. Okay, so I think laws give rise to useful functions. We saw that with mconcat. We saw that we were able to write mconcat in terms of the monoid abstraction. Okay, and if we didn't have the laws, that function wouldn't have made sense, or it would have been replaced by an entire suite of functions, all of which wouldn't have made sense. Laws allow us to refactor more. We took our string example and we pulled out a reusable function, a function that didn't even care about strings, it just cared about monoids. We were able to reuse that function, you know, with strings or even in domains completely unrelated as long as they're still monoids. So laws give rise to refactoring and reuse that we otherwise just couldn't do. Okay, and what we saw with the delist example was that laws give us tools to optimize. Okay, laws are all about being able to have two different things that give the same result, right? Maybe one's a lot faster, and with laws we can help to get there. So really what I want to say, what the default example taught us, default just overloaded a name, okay? And when I use monoid, I don't use monoid to overload the name mempty. Okay, I don't like the name mempty. I use monoid because it means something, it has laws. I can understand it, I can reason about it and work with it. And so I think laws really are the difference between an abstraction and just an overloaded name. And that's the end of the talk.